Good morning and good day to everybody. Thank you for joining today our one of the webinar series in with mining, resistivity, and IP imaging. And I hope everybody is safe and from COVID and still we're dealing with these issues. And I hope all is good and business is also going well. Today we'll We have done this before, but today we will check a little bit different compared to maybe a year ago. I did this, showing different aspect of the field survey preparations in getting good IP signals in the field. That was the most crucial part in the resistivity IP imaging, actually. And we will see in these how we can do that in manual mode, semi-automatic mode, and fully automated multi-electrode system mode, and as well as using for high power output transmitters or without using high power output transmitters, and we will see all these. So as you know, is typically is a application of mining is a most of the sulfuric mineralizations like gold, copper, zinc, and these are like mostly is the research areas in the metallic mining investigations. There is also lots of non-metallic mining investigation like construction materials, gemstones, on natural stones, like marbles and construction issues is, or like as I mentioned, gemstones is also many non-metallic mining investigations. Is generally what you do is a metallic mining investigation. You measure resistivity and chargeability together, but non-metallic mining investigation mainly you do just for resistivity. So there is no chargeability issues in the non-metallic mineralization generally. So what you use in this the measurements is I know some clients already have our systems, and some of them has different systems. And here is I can show you mainly is you can use manual mode measurement, very shallow studies, or ministering resistivity IP measurements. You can do that resistivity IP or SP. But is mostly is used is for a high power output instrument, what we call a super sting. We have a different version, 1, 2, 4, 6, and 8 channel versions. And typically is the 8 channel version is mostly used for the multi-electrode multi-channel measurement, and super sting R8, what we call it. So which is like about 200 watt power output, 100 and 200 watt power output instrument, which is sufficient most of the metallic mining investigations. And I'll demonstrate that later on. I'm sure some of you cannot believe that one single box for 100, 200 watt instrument is not sufficient for metallic mining investigation, but is not correct. So still you can use this kind of the instruments for metallic mining investigation is really get very good results. I'll demonstrate later on some field examples and how to improve that the measurement doing this. There are some cases that you can also use our power sting, which is high power output transmitter. So this is like 100, 200 watt power output instrument you can use for this metallic mining investigation. But there are cases that you want to go deep studies, or your contact resistance cannot be lowered down. In that case, that power sting, which is 5 kilowatt, 10 kilowatt, and 15 kilowatt power outputs, external transmitter, can be used together with super sting. These are you can do generally for the land, but sometimes you can also use the system under the ocean. So that the metallic mining investigation, most of the studies right now is on the surface, on the ground, or under the ground galleries. But there are cases now is the most of the mining actually is right now under the ocean. So maybe in the future there will be more investigations on this to do for not on oil and gas they are doing now, but there's also can be done metallic mining investigations in under the oceans. So still you can use our supersting system for this kind of studies and deep ocean bottom studies. Maybe we have cable system can be lowered down about 1,000 meters under the water, and then you can get this to metallic mining investigations under the oceans. So either you use this to only super sting if it is shallow studies, but if it is deep studies, it is used together with the high power output power sting and then marine super sting. For this we have this version, what we call it is the OBE1, which is the ocean bottom electrical imaging system. So there are also other instrumentation is used for mining investigation. Is this the what we call it is super sting remote? And super sting remote is mainly you use many clients in the especially for during the for not exploration, I mean the production time. Like they have this leakage studies and they put all those material and try putting water or acid in it, and they really want to study for the quality of the uh, irrigation in the area and or where the the solution material goes through, where which area is the generally for the dry areas. This can be done through those repeated measurement. What we call it is to either you take your system in the field and repeat that mining area to see the how the evolution is in the exploration productions, and also you can put that system fixed on the field. You repeat your measurements. So I didn't mention that this power sting when you use manual mode, super sting, but also you can use external transmitters with the automated mode. In that case, you need to use this power node, super sting, power sting nodes in this automated current injections. The boxes actually here. So this is another switch box grid. It can be used for any passive system for super sting, or you can use your the own cable directly connected to here, and then in the field you can also do your measurement with this. So that typically what we have is a manual cables. You do manual mode measurement, but is mainly is a multi-electrode system. What we have a passive cables and active cables. These two options is mainly used for the uh, any resistivity studies and resistivity IP studies, and especially IP studies on this dual mode. And because most of the time people prefer to use non-polarized electrodes to get cleanest signal, and especially chargeability, cleanest chargeabilities in the non-polarized electrodes through these connections. And because this dual mode has a two outputs. One is the current output, another is here on the right side. You can see there's a small port. It will be measured directly from the voltage comes from two non-polarized electrodes. So this typically can use for a multi-electrode system, active mode or a passive electrode system. When you do these studies in the ocean bottom studies and water environment, you use this actually that passive graphite electrodes in this kind of environment for the because these are the non-corrosive in a special salty water environment. Software you use in this investigation is typically is a earth imager 2D. Sometimes you do 1D if you have a 1D study, but most of the case 2D and 3D. You do like a 2D lines or parallel 2D lines or directly 3D layout and 3D measurement. You can make the processing in earth imager 2D, 3D. If you have a large 3D setup, and we have another version of the software which is 64-bit version. It is a large electrode number, large I mean the areas covering and the data numbers can be done processing in the 3D command line version. So what do you do in these systems is inject current and then turn off current, and typically over here You inject current, turn on the current, and then you measure your resistivity under here, which is primary voltage. And then you turn off the current, and then you start listening to decaying the voltage. So that's like your typically capacitive action of the subsurface. So like you're having this the chargeability. So if it is longer time, you have a better, the metallic material underneath. This decay is shorter. You have a short response coming from that metallic mining in area. So less chargeabilities or longer chargeabilities. So typically in our system, we divide this to 6 time windows. So these 6 time windows can be divided for different instrumentation and different time windows, but we come up like a 6 is sufficiently describe this decay curve. So the important in how you describe that decay curve. So the 6 time window will permit you describe that decay curve, and you get the average of the chargeability in the apparent chargeability in this 6 time window interval. That's all you do in the resistivity in IP. So when you turn on the current, you measure the resistivity on the top. When you turn off the current, you listen this charge, the voltage. Everything is voltage, but is what we call this chargeabilities in this decay curve. They're recording in the 6 time windows, and we'll give you the apparent chargeabilities, which is in general in milliseconds. So what is typically materials chargeabilities in the field? And you have, depending on your mining investigation, you have different materials like sulfuric mineralizations or some the iron and copper zinc areas, and you can see here there are the materials is like a pyrite, chalcopyrite, graphite which is about 10 milliseconds is in the depending on the percentage of the mineralization in the rocks as well. So that's the important part. For example, here 25% sulfides, it goes to 2 to 3,000 milliseconds, but you don't get that. So you generally get in the field maybe 10, 30, 60, or 100 milliseconds in the most of the cases in the study area. And I put also here is dense volcanic rocks. In most of the time, you also work in the area volcanic rock areas for resistivity IP investigation, mining investigation. You can also see that high chargeability in the zone areas. And typically 100 to 5,000, 500 milliseconds. But is the another one here is some not dense areas, volcanic areas, 8 to 20, sandstones 3 to 12. So just for reference, but every situation is different because every study area has, depending on the percentage mineralizations and surrounding rock and resistivity of the surrounding materials, and all this affecting on this the chargeability issues. So these are generally for just reference, but in your case, in every case, has to be evaluated differently. So you're not going to do like you do the survey looking for these intervals on your measurement. So your can be referenced, but just you need to consider your measurement areas can be different always. And even if they are working the same mineralization areas, from place to place is depending on the disseminations, massive and percentage and other parameters, and really affecting this chargeability issues here. So I will start with this. Can I use these stainless steel electrodes to do for resistivity IP investigations? I believe most of the people they disagree with this one, and they think is there's the uh, chargeabilities. I mean the polarization effect on the metallic structure. So that metallic polarization effect reduce your and weak, especially when you have weak chargeabilities, and you really get losing that because of that polarization effect is higher than your signal. but you can improve that in different way. Here, and I show you that screen in the first one here is using the stainless steel electrodes, and then time cycle is in the 0.5 seconds. If you see that, you can see some going up and down, and then the signal level also, that apparent chargeability about 2 milliseconds is going to some fluctuations, but in the big scale you can see that fluctuations here. But if I increase that time cycle to 1 second, so you can still get this because that over here, this is the expected decay curve. Okay, so the red is the field decay curve. So the red is the just close to black, and then you're good shape in more or less. But you can see that here, 0.5 to 1 second, you improve that the fluctuations on the noise level. But if you go like a 2 seconds, is much better. It's almost close, and compared to 4 seconds, you don't see sometimes too much improvement. So like most of the cases, 2 seconds for current cycle will be sufficient to get the clean signal and the decay curve, and in this kind of using when you use the stainless steel electrodes. So you can see also as a graphic in time windows sense. And even if you can see 2 seconds, you may see, okay, some noise level is coming through, but this is the when you go like a larger scale, and then this can be also the similar thing. So that's like this decay, you're getting it with higher when I have more stacking. Let's say when I go 4 seconds, I'm doing more stacking. So but 4 seconds takes lots of time to measuring. If I go in 4 seconds, I don't have a time limitation, then okay, I'll do that 4 seconds, but then I have to finish the one line maybe in a couple days. So if there is no time limitation, okay, you just go in 4 seconds. Even if you may go 8 seconds, and for recording and stacking more and more stacking, and then we'll give him cleaner in the decay a little bit. But optimum way you can use generally for 2 seconds in most of the cases it works in. Here's the amplitude sense and also decay curve sense. If you go like a less, you have a less amplitude, and then you may lose that signal because become very weak, especially if that polarization effect on the metals and becomes stronger than your decay. Here is that same comparison with the field data. Here's in the left side is showing two resistivity values, right side is chargeabilities. So these all images come from that article is published in last year from Gindogdu, and you can find also here to reference, and then pure applied geophysics. And we did this many years ago and in Turkey, and we compare with this to stainless steel electrode with other non-parasites that I will show you shortly. So you can also see that resistivity range, you don't see the differences when I use for different time cycles. But in chargeability sense, you can really see differences. So less chargeability, and then because dark color become more stronger chargeability values. Even if here, like a 4 seconds, it really become, and this weak anomaly is more visible. So again, is like a 2 seconds, and is optimum you can use. If you have time, it's better to go 4 seconds. But again, 4 seconds, you double up your time, because in 2 seconds maybe you're doing like a 56 or 112 electrode measurement in 2 seconds. Preparation and line and measuring, it may take half a day or 1 day. So if you're doing this the 4 seconds, maybe you're starting early, you finish in a day, but otherwise you come up the same line, continue the next day. So that's for only time consuming sense. Here I put for comparison of another decay for you when you use stainless steel, thin non-porous electrodes, and also thick non-porous electrodes. There are two type of non-porous electrode we have. We have a thin one, which is good to carry lots of them in the field, especially if you have a system for 5684, and then imagine that 84 of them is carrying this, is much easier than carrying this one. But there's a surface area of this, not big difference. Of course, this is the looks wider contact surface, but this cone surface also is almost identical to this circle area in this area. So here I show you two data points. Okay, just put two data points, and the first data point 2, you can see that when I use stainless steel electrode with thin and thick non-porous electrode, you don't really see that too much differences in the one of the data set. But other data set and data number 1, it shows a little bit difference, but they are all get the decays in easily. Even if you may think about sorry, this large non-parasitical surface, and decay become kind of a little bit noisy, you know, but in general that's normal in IP survey, and when you get this kind of the corners in each time windows, but in decay generally a little bit is like a going smooth on the top of it. So because of your increasing also the amplitude of this one, so like when you increase this signal on this one, the become looks like you get larger and then larger. So my point on this one, if I use stainless steel electrodes and then signal become a little bit weaker, looks like, but when I use this and increasing in this data set, but other data set, you don't see that difference. So the conclusion is we don't know exactly. In some points, yes, you may get differences, but still is three of these in data one is all reasonably can be used, and there is no doubt on this one. So that means is that I can still use this stainless steel and thin and then thick non-parasitos, almost same reasonable sense. Here I show you a little bit relative errors related with this one, and you can see that this relative error is in the stainless steel is like almost 6%, and the others also 6% and 9%. So you don't really see differences at all, I should say. So like a stainless steel and then large non-porous electrodes, when you use, they almost the same. So the other one is 9%, still is less than 10%. So I expect everything will be the same. So that you can use stainless steel electrodes and in these IP investigations for polarization effect is very low. Is when you use 2 seconds and more, you don't see at all the influences. In same thing. By the way, these are all like 2 seconds in comparison. If you use this large or thin non-porous electrodes, then you see almost the decay are the same. Here's another example on this comparison. Here's the left side. It shows again resistivities. Right side shows to chargeabilities. So these are all 2 seconds current cycles, and the first one is the stainless steel electrodes. Okay, the middle is the large surface, and then thin surface stainless steel, non-porous electrodes. So let's just concentrate in the right side is chargeabilities. Is that you can see that is there is a when you use this thick large surface non-porous electrodes, I have signal a little bit stronger. So you can see that is the more dark colors over here, like almost 50 milliseconds. You can see it. When you use thin one, okay, you can see that also, but a little bit less. But there is not much difference because we're talking about maybe 30 to 50 milliseconds on this. So I am all getting on these images, including in here and the same area. We have this, let's say, some indication. It clearly show better than in this large one here, and we disappear. in this one. So this is just for maybe coincidence in this case, but I mean the point is using stainless steel electrode and non-porous electrode is there's not much differences at all on these examples. Okay, how you can do this measurement manual mode is typically is all most of the mining companies ask, or the geophysical companies, they say, okay, just go and get 8 level of the IP measurements. So that's why our systems come SuperString R8, which is, gives you 8 level of measurement. Because in most of the IP studies in or dipole studies actually is the signal become disappear after the 8 levels. So that means is you got it's not disappear, but it gets very weak. So the dipole signal become very weak in, because when you go further away, and then the all signal goes to -1/r². So that means distance, it will affect your the reducing the signal. So that's why when you do dipole, you don't want to measure more than 8. Yes, there are people, they are using 16 levels, 24 levels, but you need to put maybe in this case in the 4 seconds and 8 seconds of the loss of stacking to get these weak signals. But sometimes even if you get the signal and during the measurement you don't see noise level, but when you try to process the data, is not trustable. Most of the information you collected in the more than 8 levels. So the recommendation is go about 6, 7, 8 level of the dipole measurement resistivities and resistivity IP, especially resistivity IP here what we're talking about. In this manual mode, you typically you can have this for 8 level, you can have 9 non-polarized electrodes over here. Is connected to superstring here with adapter box, and then either you use superstring directly to current injection comes from the instrument, but if you like to do high power output current injection, then you can connect the external transmitter power string in the current location. It's separate two the cables over here, and then that will become like a separated current cables and also the voltage cables in this case. So that in electrode current location you use stainless steel electrode. Potential measurement location, either you use stainless steel or non-porous electrodes, you can use it. So when you get this the decay curve under your measurement, you can follow also in tablet every decay curve of the measurement. If you especially doing manually, you can see that decay is separately, and if you're satisfied, go to the next one. If it is not, you repeat measurement. You change parameter of the current injections or improve the contact resistance, which is very important part of this the webinar today. Improve the contact resistance. I always mention all my webinars is contact resistance key issues, not only resistivity but also resistivity IP. So we'll talk about this. But you change all any parameters, and then you satisfy your measurement. You move the next one. So the next one you move either skip one electrodes moving and one electrode of half electrode spacing. Generally, I have seen that people doing this. Sorry. Doing this dipole or pole dipole surveys. In dipole pole dipole survey, you can do this kind of the 8 level of measurement. So when they move it like if you do 25-meter electrode spacing, and then they say, okay, move everything 12.5 meters. So you have to shift all electrodes manually 12.5 or 25 meters. You shift everything, you get next reading. So then you follow up this until you complete the line. So this is typically how how it is done with the manual mode measurement. So what is the advantage of this doing it? You give a full control of the signal, but it is very slow. And also it is very limited, not only for data number, but also for depth of investigations. So you just get for 8 level. If you want to improve the signal, you go deeper. Then you have to expand that current electrodes or voltage electrode spacing, get another level at the bottom, or then just getting more and deeper and deeper. If you're interested in deep measurement, maybe in this case, you get like a 100 meters dipole spacing. So you just collect the data from dipole spacing, like which like a 100-meter dipole spacing will give you half of electrode spacing the resolution, like a 50-meter resolutions. So in this case, if you have some fractures in the mineralization zone coming through like a thin layers, or the fracturing in the where the mineralization is less than 25 meters and or 50 meters, you will not find it because of the large electrode spacing. So that's for limitation on this one. But when you can do the same thing, automated mode measurements. So automatic mode is typically you use like a 28 electrodes and more. You put everything on the surface. And I'm not gonna say again here is can I use for stainless steel or non-porous? Of course, you can decide whatever you like to use it. So what I demonstrated earlier, you can use 3 options, like stainless steel electrodes, thin non-porous electrodes, and the bottom non-porous electrodes. You don't see much differences. So it still is reasonably is acceptable results. You will get it in 3 of them. So in this case, you can use that in any of them. So if I have 28 or more, and you have more electrodes, and then it'll give you for high resolution survey, because it permits you for shorter electrode spacing and more number of electrodes, and improve your resolution, and also give you for deeper investigations. And also you collect lots of data points. And then in this case, you can see here like blue colors, like 8 levels, and each color shows for different 8 levels. So we have the method also, what we call it extended dipole, which is very, very, very good for this kind of the resistivity and IP investigation dipole, because what it happen is it sometimes is the channel 8 and or level 8 and 7 become noisy in the measurement, because you go farther away, signal become weak. Sometimes you may get noisy data on the, and when you go down at the last level generally. But if we do this, the extended the dipole, this red dots also get measured inside of blue areas. All the other color, the turquoise color, comes also the inside of the red and blue areas. That means you're also getting double, not same positioning. Okay, is also getting the the data distribution is in the covering in the more areas. So this will give you more confidence, and when your time comes to for data processing, and you have a good option to eliminate some noisy data, you get much better results. But measuring time, it will increase, of course, naturally, because as a but increasing time is not double. So if I do like a dipole, maybe for 56 electrode, I will get for IP measurement in 2 seconds. I will collect about 1.5 hours in the 56. If I go actually 1 hour, but if I go for extended dipole, I will just spend another 25 minutes more, 20 minutes more to get more data points. So if you decide to use this stainless steel electrode with your multi-electrode system, and you can just put yours, what I demonstrated earlier, and you can just put it all and you do that. But if you decide to do non-porous electrodes, but you have a passive system, you don't have active system, then you can still use this in this different manner. Either you do like a 2 parallel lines. In one line is for all stainless steel current locations, another parallel line is all non-porous electrodes, or another layout, what we call it serial layout. So you just can and every single electrode is current. Even numbers and odd numbers is the current, even numbers is here in this case is the voltage electrodes. So you can just like do this way also what we call serial layout and using these non-polarized electrodes. Okay, if you have an active system, which you really get uh, option of using these non-polar electrodes, because this dual mode, what active electrode permits you inject current through these stainless steel electrodes and then measure the voltage decay voltage over here, separate it from the non-polarized electrodes. So like here's a typical the field survey area is here is connected to non-polarized electrodes. Here's the current locations. So if this electrode use current injection, just inject current. If this used for measurement, so measurement just from this electrode it becomes. So this is much clean signal you can get it for compared to passive systems, but it's more expensive and in the sense that other and more delicate. So you have to be a little bit careful, and because each end uh, electrode has inside its own electronic board, and then you don't want to throw it away in the field to get damage on this one. So it's much easier to use in this non-parasitic when you want to use it. You can use together, and this is a very good option to get very good signal and clean signal compared to the others in the in the studies generally. So that this the array type you can use same thing in dipole or extended dipole or pole dipole, which is typically for mining investigations can be done. The another option what we call it is the semi-automatic mode. So what you do is you put all your multi-electrodes on the surface, and then you put your the current injection through manually all current locations. So what you do, you just instead of in manual mode you need like 9 potential electrode and then 2 current electrode locations. So that means you need 11 people in for manual mode measurement, because 11 people has to move and at the every measuring locations. But in the when you do semi-automatic mode, in this case, you just lay out your multi-electrode cable and just 2 people and current people they are moving. So that means in each time you inject current, you measure an instrument stop, and then they change the current electrode position and then get measurement. So that also be done what we call it semi-automatic mode. But is the most reliable things is to do everything when you have let's say system available. Use a external transmitter, power outputs, high power outputs, and use power nodes, which is the permits you to inject high power output current from the power sting. So then you can inject the current directly from this external transmitter through the power nodes. Okay, so then measurement can be done directly to your multi-electrode cables. So this requires typically 2 parallel lines. One line is the for power node cable, what we call it, power sting line. Another line is potential line. So you have a 2 multi-electrode cable. One is the for this multi-electrode cable for the voltage, and only for a multi-electrode cable for the power node cable, actually what we call it, and then here. But here is an example shows a 84 electrode system, but here you don't need to do let's say 84 power nodes. So typically is a 1/4 of that the number of electrode, the power node will be reasonable generally. But if you have like 11, more than 11 power nodes, still you can do this kind of the survey nicely. Here's one design, and I did one of my client actually in Africa. Here you can see that they use this power node line over here, and then this picture come from them actually, that they are doing these mining investigations in Burkina Faso, and they can do these kind of things in like this using this power node and through the power injection. Then you collect with deeper data points over. So you don't want to go through like these shallow data points. So that's all the potential electrodes is showing here, and then you will get all these let's say the measurement with through the high power output transmitter and automatically. This typically recommendation on this is while you're setting up your either you do this passive cable system or dual mode cable system. Okay, so while you're doing this to preparing those line, what you do in the field, first you prepare your passive or multi-electrode cable line, and then just with instrument supersting you get just for uh, let's say 8 level or 16 level of this shallow measurement through the supersting. So meantime you prepare the power node cable, power node location, power sting. When it is done, you collect this data and later on combine both of them to make complete, like this is the resistivity IP measurement with combination of the external transmitter power node. There are many different things you can make this improve the contact resistance. Here on the left bottom here, you can use a bentonite solution, putting this bentonite solution that keep the moisturized, and especially for current electrode locations. You put this, it will keep the moisturized in whole day, not whole day actually. It remains there a couple days. Here, right side, you can see that there's a remaining of this the area prepared with now that the the bentonite solution after 2 days still is wet. So especially the study areas in hot areas in the Middle East, in some hot areas, it's a good option to use this to moisturize ground and keep that ground is moisturized, and then keep that contact resistance is always low. And if you don't have this option, you can also use this here on the left, a small let's say a plate, metallic plate, or you can use this aluminum foil, and then put aluminum foil, maybe 30 by 30 centimeters aluminum foil, and put your stainless steel electrode top of it, and then put the mud and water it, and it also lower the contact resistance. So especially these are generally for current electrode injection locations, okay? Because you're not gonna put this aluminum foil doing your IP measurement, okay, just for current injection. The another one here, using more than one stakes. If you have more stakes, you can connect it. So this will also improve your contact resistance areas. Put on water, salty water when you do for only the current injection on these electrodes. But if you do like a pole dipole measurement, we recommend to put that pole location like this over here. Let me just go pen laser over here. If you do like this pole electrode locations, and then just dig like a ditch like this, put lots of water, salty water, or bentonite solution, whatever you have, and then because this electrode is in pole dipole measurement used for current injection for every measurement, okay? So if you just put just one electrode like this, it will dry out in after a few measurements, because of you're heating up the ground every current injection. You're putting maybe 400 volt, depending on the transmitter, or more. If you're external transmitter, maybe we're putting 1000 volt or 2000 volt in this, and then you're heating up drying up the ground. So to avoid that drying up, when it is dry up, it will increment the contact resistance. So when the contact resistance increment, and then you become a less current injection, and then become like a noisy data. So you start everything good, but later on everything it gets worse. This is the I have seen lots of clients, they don't pay attention on this, and then just put all multi-electrode system and then push the button and get measurement, and then later on that contact resistance increase and make everything worse. So to avoid that, just keep this poly-electrode location moisturized during the whole survey. Like a bentonite solutions, aluminum foil, or more electrodes connected each other, they get more surface to contact in the ground, lowering the contact resistance. When you use these non-porous electrodes, you're not going to use this salty water or bentonite, because those are like a salt. If it is not very salty, then I mean the uh, less conductive bentonite, if you can find, you can also use for this. I mean, there are different options of the bentonite solution. Bentonite can be fine. Some of them most of them are very salty, right? Very conductive. But if you get less salt in that, and then you can use also for non-porous electrode locations. But it's typically you need to do just a simple water and then put on clay, and just to get this moisturized ground and put this non-porous electrodes, get good voltage readings. But current electrodes also important to inject more current. So you follow up this, what recommendations you really get for a good current injection. When you have a good current injection, you have a good signal. So what is my contact resistance should be? Generally, for it should be less than 1,000 ohms. If you can do that, then you really get good resistivity IP measurements. But sometimes it's not possible. But in our system, okay, it is better to consider less than 2,000 or 1,600. But I will share. I should say that if you can lower it down much lower, that would be much better. So if it is less than 100 ohms, 1,000 ohms, sorry, 1,000 ohms, and you really get good current injections, either super sting or through the external transmitter. So it doesn't really if they matter too much in this case. So I can use the super sting 200 watt power output or 100 watt power output super sting if I'm using normal mode. Then I can really get good resistivity IP chargeability data. So, but if your contact resistance is high, and then I am now limited with the current injections. So if I'm getting less current injection, I cannot charge the ground sufficiently. If you cannot charge the ground sufficiently, then you don't get good IP data. So the key point always is to reduce the contact resistance and then make a good injecting current, get good chargeabilities. Okay. Here is another option to do like a 3D. Either you do parallel lines, and like parallel lines, you get it and then make 3D, which is the same thing like a 3D, or you just get like this the 3D layout. Put like a power nodes, any shape, rectangular on around it inside, and then you just draw your like a 3D grid, and through the multi-electrodes, you can collect also 3D resistive IP, fully automated mode. Okay, you can do full automated mode, semi-automated mode, and manual mode is not. There is no way. Sometimes it's very complicated, but still you can do that if you control it. But it's not easy. Here's a field example, just showing the comparison with different, like what we did. I showed this earlier, but one more time, showing stainless steel electrodes, thin non-porous electrodes, fat non-porous electrodes. Here's the high chargeability areas. It really shows in all three of them. Maybe is a shape. Sometimes the misleading. Because to become at the bottom is not sometimes very good high resolution data you can collect. So maybe this is concentrating over here. This shows a little bit large volume, and then this one also going large volume. So you may ask, okay, which one is right then? So I think it's all of them right. Only thing is you need to drill and then get this confirmation. and we don't know where exactly this ending over here. Maybe this is just is a caution generally. You just get like in the more or less here on the upper part. So bottom part is generally is you don't have sufficiently signal to get better resolution to define how deep this anomaly goes. But it's definitely this anomaly is located over here, and from the top it's going there, and then where it is end, to find out that you need to drill out. So the same area is done also with the parallel super thin line, I mean the stainless steel line, and using the thin non-porous electrodes, and also the using this in parallel line shows you this in similar way to the to get these chargeabilities. Now I'll show you a couple more some case study examples, and then we are done here. So I don't want to keep you more. Here's another examples come from this one of the clients. They did is a iron ore. This is very shallow study actually, but it is used for stainless steel electrodes, and I think 5 meter spacing, and you can see that the high chargeabilities, low resistivities zone over here, and high chargeabilities in the area. So like typically what you're looking for most of the time, high chargeabilities, low resistivity zones most of the time. But sometimes you're also looking for high resistivities, high chargeability zone areas. There are some areas also, mineralization areas, like the granites in the areas in where it gives high resistivities inside, and there are some the gold nuggets inside, it also give high chargeabilities. But this is not that the one I'm talking about. This is just for the iron ore, gives you for low resistivity, high chargeability. This is another example come from the Canada, is and also there's kind of the fracture is going over here, looks like, and low resistive zone, and then you can see that this the high chargeability area, it shows like it in this way, but is typically is they highlighted on this area only for where the mineralization is concentrated. So this, if you go deeper and the information you're getting is broad and you don't really know concentration. So there's resistivity in IP service most of the time is not easy to get for deep in local information. So you get information in broad sense and you need to interpret it somehow. This is one of the interpretation they did it, and they get the gold in this area. So there is indication of the low resistivity, yes. There is indication of the high chargeability in the area, yes. So you drill over here, you get it. You drill over here, maybe in this high chargeability zone area is not getting. So but concentration maybe over here a little bit. So that's also that gives you, don't trust whatever you see always. So you have to check it. So checking point is drilling. When you drill, you really get your result, what you interpreted. So this is another is like a 3D has been done like a parallel lines, many parallel lines, and combine, and each line about a kilometer long, and then you can get like a 3D layout almost. Maybe if you go this way another kilometer, and you get like a 1 by 1 kilometer. This is not the case, but this is just 1 kilometer by to, I think is here about 300 to 400 meters wide in the area, 3D area. So it will give you this an upper figure shows the chargeabilities, the resistivities, and bottom over here show the chargeabilities. So in the 3D, and you can see, okay, this is resistivity, this is chargeability. In 3D, you can see that this high chargeability zone, and you can also highlight wherever you want to concentrate your anomaly, and then you can really make also the estimation, gold estimations, or the mineral estimation in the mine estimation in the area, reserve estimation, I should say. So this is also can be a very useful tool when you time to comes for some estimations. Actually, just doing the resistivity and IP survey. Okay, this is another case is for controlling that, like a heap leach mining copper. They did many parallel lines on that leakage in the area, and they want to know that where the irrigations is in what they are doing is control. I mean, it affecting whole area or not. And then they do some resistivity survey on the top of it. They found that irrigation is really as showing where the saturated zone, and also some areas still didn't get any irrigation. So there are some dry zones in this in the leakage study. So they need to maybe drill here, inject more liquid or acid, and to get at also the mineralization from these dry zone areas. So this is kind of controlling for your the mining process, so that it will help you to identify in during the production of that in the heap leach, sorry, in the mineralization areas. So this shows typically 3D highlighted where the dry zone exactly locations, and pinpointing all these dry zone, and then that will be easy now to just drill maybe over here, inject more liquid in the area, and then get this also the information. So the next one, it's typically is non-metallic mining investigations case studies. I will show you in here. This one is kind of the river paleo channel studies here. You can see some paleo channel high resistive zone areas, and then they want to do for some construction material getting from there, or could be in paleo channels in most of the times also important for mineralization. Like I have seen clients doing some riverside paleo channel studies for trying to find gemstones in these paleo channels in this kind of paleo channel areas. So this really shows you where your unit the located or more resistive, high resistive zone areas, and where the paleo channel is located, and then you can get this either construction material purposes or gemstone purposes. You can get that information through doing resistivity. So in this case, you don't need to do IP studies. Resistivity will be sufficient because there will be no material to give the chargeabilities, because then all that's non-conductive materials generally you're looking for. I think that's all I can tell you today about for all these resistivity IP investigations. And if you have any question, you can contact us anytime, and then you can ask any question. So I see this morning somebody asked about one question regarding about the coal mining and what resistivity IP studies can be done. Well, I should say that not only coal, but all studies has to be evaluated separately because of you need to know how that geological lithological structure in the area. And I know more in some areas in the coal investigation is like a repeating of this lots of the sediments and clay, silt, sand, and then lineate in the area. Sometimes you really get lots of the repetitions in maybe 3 meters in clay, and then 2 meters in the coal, and then 1-2 meters in sand, and that will repeat. So in such cases, maybe it is not easy to identify that 3 meters and thin layer coal, which is the typically organic material, and will give you this the high resistive areas in the places. But sometimes it will give you about I have seen some other areas also get like a low resistive the call informations, but you don't get in general for IP in this call location. However, there are cases also I have seen that for the core areas and not become a rock, it become more or less just kind of the moisturized with area and become kind of liquid. In such cases, but these are shallow studies, and there is case study like this in our web page actually. In that case, yes, you can do resistivity IP, and it really gives you very high chargeability. All those thin, I mean, for the coal material is not become coal anymore, but it's kind of the kerosene. So that like a wood is under the ground, with the long time become like a kind of the all organic material become a coal in the pressure and temperature. But then sometimes it's not special the sufficient sometimes temperature, and it is with the wet area kind of a little bit liquid, like a Khorasan. In that case, there is an IP information can be detectable, but that's generally for what we call it is for contamination purposes, DNAPL studies. But for mining purposes in the coals, if you're looking for 100 meters depth in the coal layers, lignite layers generally, is depending on the thickness of that materials mine, and also the depth is the determinant factor. Can be done maybe there are examples in the coal mining areas is like 70 ohm meters, 2 ohm meters resistivity values, but there is no chargeabilities in such cases in this. But you most of the case, if you do resistivity IP, you get the chargeabilities surrounding that. Typically there are always clay and silt in the area. That clay will give you that chargeabilities, not the coal material. Well, anyway, you can always send me your uh, you can always send me your questions anytime, and I can answer. And I'm available through the emails, and also that we have available online, and we'll be happy to answer anytime. So I'm just sending in Paul. You can answer all those questions. I put some questions there. You can get some feedback also. That will be very good, and I appreciate it. Well, thank you very much for joining my today webinar. I hope we all see you in the next coming webinar in very soon. Well, thank you so much, and have a nice day. Bye bye.